Hello, everyone, and welcome to our talk. And thank you very much for inviting us to this NeurIPS workshop on robot learning. And so today I will share my talk with Rika Antonova, who's a postdoc in my lab. I will introduce her later. And let me just start by saying that today I want to talk about the challenge of robot learning for manipulation of deformables. So this can be any kind of deformable objects like any kind of clothes or wires or ropes or even granular material. So these are very difficult objects to manipulate. And so just in general, my research is driven by this question of why humans are incredible at manipulation tasks. And it is fairly unclear what the underlying principles of this robustness are, both in execution and learning these skills. And it is even more unclear how these principles can be transferred to robots that have a completely different embodiment. So what is the goal, again, of a manipulation robot? So given any kind of sensory information, so here, for example, pixels through a camera, the robot needs to choose control outputs, let's say here motor torques, such that the environment reaches some desired state. So let's say such that the robot can actually reach for this drill here on the table. So the state will then be perceived again in the next control cycle to choose the next motor torques. And that means the robot needs to know a policy pi here that goes from, in this case, pixel to torque or any kind of sensory information to torques. And so in grasping a manipulation, all these kind of changes of the environment happen through contact interaction. So of course, you also don't just necessarily want to pick the next best action in the next, let's say, millisecond, but you may also want to plan ahead over a longer time horizon than just this millisecond. Okay, so let's omit this planning stuff for now, and let's just ask ourselves, why is controlling this robot so hard again? Like, what's the problem really? So just for a quick back of the envelope computation. So let's say this particular robot is called Apollo. Actually, it has 25 degrees of freedom, or joints in this case, each of which needs a motor command at every millisecond. So even if the command for each of these joints has only 3 possible values, so let's say forward, backward, and 0, there is a combination of 3 to the power of 25, which is kind of 10 to the power of 11 possible different actions that can be taken in every single, at every single moment for every single millisecond, right? And so that is an incredible amount of possibilities. And of course, this is already a simplification because in reality, the action space that we have to pick from is continuously valued and therefore infinitely valued and not just 3. Okay, and so now let's make this even harder. Remember, sometimes we even want to plan ahead multiple steps and you have to search the entire sequence of action over this maybe longer planning horizon. Okay, so clearly this is unmanageable coming in without any kind of structure. And so I would argue that to make this actually manageable, we need some kind of bias or structure to focus either learning or optimization, in this case of good manipulation actions, into a good area of this vast space universe of possibilities, okay? And so the approaches that we are taking at my lab, at the Interactive Perception and Robot Learning Lab, are a variety of ideas on how to make optimization and learning in these large spaces actually feasible. And so one particular area that we have been exploring for a while now is to actually make algorithms like filters or smoothers differentiable, and not only just algorithms but also just physical models like renderers that encode projective geometry or physics models that predict over in time, make these also differentiable, embed them in simulators, and then when optimizing models that actually feed into this, differentiate the loss through all of these algorithms or models. And we've shown that this critically enables not just data efficiency, but also a bias that introduces less variance under, for example, distribution shifts. Right. So another kind of approach or direction we take a lot at my lab is by doing learning from demonstration. So specifically, recently we looked a lot at the problem of how can a robot learn by watching a person. In that case, the challenge is that this robot doesn't have access really to the underlying joint states of what the person is actually doing, but only sees what the person is doing and what the effect of it is. And the question then becomes like, how does the robot imitate this and maybe achieve a similar desired effect? So we looked at lots of our recent work has been looking at this. And the reason for this is that videos of people, for example, demonstrating certain manipulation tasks are actually quite widely available. So it would be great if we could avoid any kind of teleoperation or kinesthetic teaching approaches that are hard to scale up and maybe tedious, and replace them by robots learning by watching people just in videos. And then in my lab, we also looked a lot at how we can actually exploit the multiple sensor modalities that a robot actually has access to for learning better skills. And so for learning-based approaches, this is particularly interesting because increasing the number of modalities at the input of these models may make certain states differentiable, or not differentiable, but you may actually be able to separate certain situations or certain states in the state space because you have suddenly access to other modalities. So let's say you're trying a context-rich task, and before the robot only had access to visual information, then a situation or a state where the robot is actually in contact or just about to make contact may look visually very similar. But once you add, for example, the sense of touch, you can actually really distinguish these two cases. So envision and touch is just one example we looked at. We are also looking at including sound, language, depth data, and so on. And another thing that multiple modalities offer is actually new supervised losses to train, for example, state representations. All right, so lots of the work that we have done is actually dealing with the manipulation of rigid objects. And more recently, I became really interested in manipulation of deformables. And so here are just a few examples of applications that show where we as people have to deal with deformable objects all the time. And it's really ubiquitous. So it might be useful for a robot to also learn how to manipulate deformables so that they can be useful in either surgery, food processing, search and rescue, domestic services, like, for example, just doing laundry, wiring, or wireframing, like this person in the middle is doing, or just helping people to get dressed and so on. And so I will now hand over to my postdoc, Rika Antonova, and she is really an expert in active learning of transferable priors, kernels, and latent representations for robotics. She has done lots of work in this area. And more recently, she's really interested in working on deformable objects and enabling a robot to actually perceive, manipulate, in the sense of controlling and planning deformable objects. And yeah, with that, I hand over to Rika.
Thank you, Jeannette, for introduction. Let's take a close look as to what is interesting about deformables. They have a large state space and potentially an infinite number of degrees of freedom. And also, annotations for full supervision are very difficult and expensive to obtain. So we need self-supervised or unsupervised methods. But what happens if we learn low-dimensional embeddings with such unsupervised methods? There are still the challenging dynamics that remain, so both this learning is difficult and then using the learned low-dimensional state is challenging. And occlusions and high deformability make similar states look unfamiliar, whether it's a higher dimensional representation or a low dimensional embedding. So the data efficiency of methods that are made for rigid objects deteriorates quite significantly. I will talk about two of our recent methods for manipulation with deformables, and starting with Bayesian treatment of real-to-sim for deformable object manipulation. So here we take a Bayesian approach to real-to-sim and consider this as a problem of probabilistic inference to find parameter posteriors and avoid committing to a single set of parameters. And this is crucial because in case of noisy and complex dynamics, we can't really expect that any single parameter set will make the simulation behave exactly like reality. So unsupervised methods, they may learn heavily simplified and noisy approximations to the true state of the deformables. And our insight here is that we interpret this approximate state as a probability distribution. Then with the representation that we are creating, we achieve permutation invariance and also a representation that is more resilient to occlusions and noise. And overall, our approach allows inference from even a single trajectory, and we can adapt to changing dynamics by getting new posterior estimates as the new real-world data arrives. So as a new trajectory arrives, because we can do inference from a single trajectory, we can kind of refresh our posterior. So first, let's take a look at the hardware scenarios we will consider. This is a winding task where the point is to wind the rope around the spool. And this is a fling task to fling the cloth into the air and then spread it out on the table. And this is a wiping task where the objective is to wipe the table with back and forth motions with a slightly deformable cloth. And we're using Intel RealSense camera to record. This is an example of how our simulation looks like when we sample different parameters for bending stiffness, elastic stiffness, friction, and scale for the winding task. And this is the same thing for the fling task. You can see variability here in how the cloth behaves. And this is for the wiping task. You notice that we here paste the very realistic looking background. So we're trying to bring the sim and real close in terms of visual appearance, but we consider the dynamics that are very, very different, and we need to align those. So for that, we develop an approach that we call BaseSim RKHS, and I will explain it here. First, we sample simulation parameters from the prior and then collect simulation trajectories. Then we extract the key points. Then we apply the RKHS net layer that I will explain in detail. We observe that key points are unordered and they can appear on different parts of the object. So we interpret them as noisy samples from partially observed state distribution. And we embed them in an infinite dimensional space in a non-parametric way. And this way we get permutation invariance, we get robustness to noise, a convenient distance metric, and also continuity of this mapping. We'll need a little bit of background to understand how this embedding is done. So there's something called mean embedding, mu sub x, that can map a distribution into an infinite dimensional space. And I'm giving here the reference to the paper that introduced this. And so this can represent the probability distributions basically without loss of information. And technically this means that mu sub x can recover expectations of all the functions in a given reproducing kernel Hilbert space, and this can be done with a dot product. Now, we can compute this mean embedding from samples, so from a finite number of samples. And this is a kernel method, so actually this gets a little bit expensive as the number of samples grows, so more than quadratic, so usually it's a cubic method, and so we would need to approximate this in order for this to be computationally efficient. And this can be done with something that's called random Fourier features. I'm giving the reference here, and I'm going to quickly describe the basics of how this is obtained. So the kernel can be approximated as a dot product of the finite dimensional features so that we can actually compute them explicitly. And the way that we get this is using Bochner's theorem. We can see that shift invariant kernel can be represented in terms of its Fourier transform. So this is what the theorem states. Shift invariant means that the kernel takes as input the difference between x and the second input x prime. Prime here doesn't stand for derivative, it just stands for another input. All right, and for real-valued kernels, this actually simplifies to the expectation of the cosine written out there. And this P of omega here is the spectral density corresponding to the kernel k of x minus x prime. Right, so what can we do with this expectation? We can approximate this with Monte Carlo method, and with that we obtain basically this finite sum. And the m here is the number of features that we choose, so the granularity of our representation depends on this number n. And finally, we can rewrite that sum as actually a dot product of phi hat and phi hat, and then this phi hat is a vector of cosines and sines of dot products of this omega and our inputs x. And this omega here, when it's sampled, for example, from normal, this overall can approximate an RBF kernel, and there are other distributions that you could sample from, and the result would approximate other kernels. Right, so with that, we have our RK-Chestnut layer. This boils down to computing the following vector here. And we note here that we have additional parameters like the sigmas, which have to do with the variances of the Gaussians if we're sampling from the Gaussian density, and omegas, which are the random features. And they can be also adjusted via the gradient descent, so that we have a seamless backpropagation through the whole pipeline, and we can adjust the frequencies, adjust the additional parameters like sigma, and propagate this all the way through to our representation that we're learning. So with that, we train the BaseSim. BaseSim is a method that is described in this reference number 3 that I'm giving here, which overall allows us to use the simulated trajectories in order to then create a sort of an inverse mapping from trajectories to simulation parameters. And then with that inverse mapping, we can condition that on a real trajectory. And with that, obtain, after this conditioning, a posterior from which we can again sample. This posterior over simulation parameters is going to be a bit more peaked, and then we repeat again the whole process in the loop. So this way we can iteratively actually arrive at better and better estimates and sample our simulation around the regions which is more and more like reality. Here I'm illustrating a few results that we've obtained with unsupervised key points on the left and the supervised key points on the right. You can see the representations are pretty noisy because it's ambiguous as to where these key points should be placed on the row. And nonetheless, when we look at the sample from our posterior distribution and the alignment between that sample and what happens in reality, we get a pretty good result. This RK-Chestnut layer that we have introduced here, it gives us a significant boost in performance over the BaseSim method that was working without this layer on top of this very noisy representation. And this is the result with the supervised key points, similarly reasonably good alignment. This is visualization for the unsupervised and supervised key points for the fling task. And this is the real to sim alignment, similar evaluation here. And this is for the supervised key points. Right, and this is for the wiping task here. Actually, I'm illustrating on the left that the unsupervised key point learning wasn't able to ignore the robot, whereas on the right, the supervised key points were able to do that. And so for the unsupervised case, we got a slightly less aligned, you can see the angle there in the cloth, slightly less aligned result. And with the supervised key point, you can still get a pretty good alignment. Now, notice here that, of course, the match is not perfect. For example, here the cloth is a little bit larger, and that is because this is just an example of a sample from the posterior. So the mean could be perhaps perfectly matched, but when you sample, if the posterior is not very narrow, then you can get samples that are slightly different from the mean. We are going to continue using the unsupervised key point learning method in the next work, where we look at the case of not having access to simulation and learning directly from real data. In this case, we consider the problem of learning from a single video of a person doing a long and repetitive task and no robot demonstrations. And we want to make use of periodicity to improve learning. Also, we are going to do the unsupervised learning of key points, but now we have an additional challenge of removing the dependence on the embodiment. So human hand manipulating the object versus the robot gripper. This is the overview of the approach. We start with the human video, then we partition it into periods using an existing approach called RepNet. And then we do the unsupervised learning of the key points, and then we learn the optimal policy for the task. So for the key points, we take a human play data and robot play data. And that play data is just unstructured interactions with the object, like here, the wiping cloth, for example. We mask out the human arm and the robot arm so that the key point representation learning network can focus placing the key points on the object as opposed to the arm or the robot gripper. And then what this gives us overall after training is a distance metric that we can use in Bayesian optimization. This distance metric is how well the key points align since they are placed on the object and they're independent of whether the human arm is doing something to them or the robot arm is doing something to that object. Now we can take a look at how we are going to learn the policies. For this, we're going to use an algorithm called Bayesian optimization. And for those who are not familiar with it, I will briefly introduce the necessary background here. So we're considering the problem of finding an optimal controller x star such that some objective function f of x star is maximized. And we're going to keep track of the mean and covariance of our estimate of what the objective function, what we know so far about this objective function. And this posterior is going to be modeled with a Gaussian process. Now, what is a Gaussian process? Well, formally, there is a formal definition as a time-continuous stochastic process and so on and so forth. But actually, if you want a pretty intuitive and visual introduction into it, that there are plenty of resources out there, and I'm linking here one of them with very nice visualizations. Here, I will mention the pieces that we would need conceptually to understand is that Gaussian process provides an interpolation between the points that we already know about, so x's that we have already seen. These x's in our cases would be the parameters of the controllers that we have already ran in the real world. And this interpolation would let us predict, okay, what would be the output of this objective function on the controller that we haven't executed before, the x, unknown x, and one of them is x star, which is the kind of the optimal one that we're looking for. And then the second aspect of the Gaussian process that we're interested in is the variance, and this is to capture the uncertainty over our predictions for this objective function. So now the Bayesian optimization has another component that is called the acquisition function. And this acquisition function is going to take a look at the Gaussian process posterior and from this decide what should be the next promising sample to take, aka the next promising policy to try. And then ultimately what it's going to do is it's going to be focusing the samples more and more on the promising regions. So let's take a look at how this runs. So we start with one sample. The acquisition function suggests a few samples to reduce the variance globally. And then as the variance has been reduced, it samples closer and closer to the parts where the posterior mean is predicted to be pretty high. And you can see that some parts of the space here are left unexplored because it is unlikely that they would be better than the optimal region that we have found so far. So this way, what we achieve is that we achieve being able to search globally. So we will reduce uncertainty globally, but we do not overexplore the regions that cannot or are very unlikely to beat the region that looks most promising. So that's it for the basic background on the Bayesian optimization. Let's just look at this visualization one more time. Now that we roughly know what is supposed to happen here, right? So you can see that it is zeroing in on the region where the posterior mean is high. All right. So now, coming back to this, so we will use Bayesian optimization. First sample is going to be random. We're going to sample a bunch of waypoints. And then from these waypoints, we're going to fit a rhythmic dynamic movement primitive then unroll this into basically an open loop execution policy. And then this policy is going to generate for us interactions of the robot with the deformable object. From this, we're going to get the video, and then we're going to compare this with the human demonstration. But we're not going to be comparing pixel by pixel. What we're going to do is we're going to look at how the deformable behaves in terms of where the key points are. And with that, we have an effective way of comparing what happens to the deformable when the robot manipulates it versus when the human manipulates it. So we get the score. And then this is our f of x, of unknown x. Now it is known. All right, and then we put this evaluation of x into the Bayesian optimization posterior. And then, as you have seen now in the illustrations, the acquisition function would sample for us the next promising sample, so another set of waypoints that we will use to fit DMP, rhythmic DMP, and so on and so forth. And the rhythmic DMP aspect here is because it's convenient for us to be able to roll out this DMP over the multiple periods, to scale it also, and we will show some convenient properties of this representation for the policy later in the videos with the results. So here's an example of how BO runs. We start with the human demo that is doing wiping. On the first trial, okay, we have some semi-random behavior. By 15th trial, we have something resembling the wiping. And by the 30th trial, we've basically replicated what the human is doing in terms of the motion of the cloth. Now, Bayesian optimization is designed to be data efficient, but with deformables, we still need to help it out a little bit to achieve the sort of data efficiency that we're used to with rigid objects. And for this, we are going to reuse here the play data that we have already used for representation learning for key points. And what we're going to do here is we're going to take the play data and randomly segment this kind of trajectory overall of this play data, and then also randomly recombine these segments. And from that, we're going to obtain a bunch of different pieces of trajectories, and these trajectories we're going to score as to how well they do on the first initial period. And if they do well on the first initial period, that means that when we unroll the policy over multiple periods, that they're likely to do well overall. And so we add them to initial candidates, which we are going to use for Bayesian optimization to kind of get a warm start. And so with that, what we have is, for example, for the other task, like winding, we're also able to reproduce the behavior of the human, again, in terms of what has happened to the objects, not the arm or the robot gripper. And this is an example with the stirring task. And here you can see the tracking is just on the tool. We're not tracking the food there. Now, one good point about this policy representation is that we can unroll it over a different number of periods after training, and we can scale the motion to make it larger or smaller. So here is an example of making the motion smaller and just doing 2 periods instead of 3. So with that, overall, what we have is that we can make use of self-play to improve the data efficiency of both building the representation and also of the active learning part of the policy optimization. And we use the Bayesian optimization here to actively refine this policy, so essentially the robot makes autonomous decisions as to what next strategy to try. And this gets us closer to autonomous robot learning, which is guided only by videos without any annotations or metadata.
Yeah, so with that, I want to close this talk. Thank you, Rika, for the great detailed explanation of the work you've been doing with students in the lab. And with that, I thank you for your attention, and I thank also my funding sources.